Jamie Knight is going to talk to us about optical properties of aerosol particles.
So hi, I'm Jamie. I do my PhD at Bristol, supervised by Michael Cottrell and Andrew Ewing. And my project explores the optical properties of aerosol particles using single particle cavity ring-down spectroscopy. And specifically, we're interested in absorbing aerosol particles. So aerosols in the atmosphere, they can absorb light, and that has a warming effect in the atmosphere, or they can scatter light back to space, which cools down the atmosphere. And the extent to which a particle will absorb or scatter light is dependent on the particle size, morphology, and also on the complex refractive index, M, which is the sum of the real refractive index, which really broadly tells you about the scattering of the particle, and the imaginary refractive index, K, which tells you about the absorption of the particle. And so why we're interested in these properties? Well, the relative forcings, which are the kind of net kind of change in energy in the atmosphere due to these particles, is dependent on the complex refractive index. And if you look at the organic carbons, these kind of things that we're really interested in are really atmospherically relevant at the minute. They have a really large uncertainty in their radiative forcings of maybe, I don't know, 75% or so. And a lot of this uncertainty comes from the absorbing part of the aerosol. I mean, there's been these nice studies say that you need to know the imaginary refractive index to within roughly 0.001 for calculations of radiative forcing accuracy to plus or minus 5%, which would obviously be a nice improvement on the radiative forcings here. So kind of compare back to this value later at the end. So the experiment, single particle cavity ring-down spectroscopy, we send a kind of packet of light energy into the cavity. It's defined by these two highly reflective mirrors. The light traverses back and forth in the cavity between the two mirrors. Some of the light leaks out and is collected at the photodiode, and then the time taken for the light intensity to decrease to 1/E, the original intensity. We term this tau naught here. When we introduce a particle to the laser beam, you get some additional extinction from the particle, so that scattering and absorption processes, and we term that tau. And the relationship between tau and tau naught can tell you about this extinction cross section, which is the total power removed from the incident beam by the aerosol particle. And we can use optical models to separate this extinction into the scattering and absorption properties. So how do we trap the particles? Previously we used optical traps, but when we want to look at absorbing aerosol particles, we need to use something else, because photophoretic forces kind of dominate and force the particles out of those optical traps. So we use these linear electrodynamic quadrupole traps. You charge the particle, send the particle into the trap. The quadrupole stabilizes the particle in the plane of the table. You can see that the pairs of rods are connected, and each pair is phase shifted by 180 degrees. We apply some AC voltage, creates a electrical potential minimum in the center of those quadrupoles, which stabilizes the particle. And then in the vertical plane, we have this ring electrode at the bottom. We apply some DC voltage, which is the opposite polarity to that of the particle, and that stabilizes the particle, balances the droplet weight and the drag force from this N2 gas flow from the top, which we use to control the relative humidity in the chamber. So putting that all together, we've got our ring down beam, we have our quadrupole trap, we stabilized our particle. We also want to know about the particle size, so we have this Gaussian illumination beam propagating upwards, and we collect the perpendicularly scattered light at its objective, and you get something that looks like this. So you get these nice intensity or angular dependent intensities, which come from the interference of the scattered waves. And these are characteristic of particle size, so we can compare them to meteor simulations to determine the size of the particle. And so we can plot something that looks like this. So this is for a pure component particle of hexane trial. It's commonly used to benchmark these systems. It's non-absorbing and it's semi-volatile, so that's what gives us this radius change. And you can see it's a pure component system, so obviously the complex refractive index is constant over the size range. So anything that's changing here is the radius. You get these nice size-dependent sharp resonances, these really sharp resonances here, which are a key feature for this talk. And they come from these whispering gallery mode resonances. So you get at certain particle size, you get efficient coupling of that light into the cavity, and they give you these really sharp increases in extinction. And when we add an absorbing component, which shows you on the next slide, if you think of the particle as a kind of resonator, the quality of that resonator decreases as you add that absorbing component, and we'll see these sharp resonant structures broaden and flatten in size. So here I've added a nigrosin dye, which again is just a common dye used to benchmark systems. It's non-volatile, so only the hexane trial is leaving the droplet. So on this top plot here, this WN is the mass fraction of the droplet of nigrosin in the droplet rather. So it's pure HT on the top there, hexane trial, purely scattering. We add some small amount of nigrosin dye. You can see the resonance structure decreases, and some more nigrosin dye in the resonance structure is almost completely removed. And what we can do then is we can use me theory to predict what these extinction cross sections are. So we put in our values of particle radius, and we do a grid search over a load of different values for the real and imaginary refractive indices. And then we compare each of those plots to our measurement and find our best fit solutions. So I think I've deferred showing you what these changes in the imaginary refractive index of size are until the end, because these are the first measurements we've ever done for absorbing aerosol particles using single particle Calturian spectroscopy. So what we wanted to do first was to determine the accuracy of these assessments. And what we do is we generate these theoretical data sets with known inputs for N and K using me theory. We then superimpose some fundamental noise, which is proportional to the standard deviation in the tau naught values. That's related to things like the accuracy of the photodiode detector and changes in radius scattering in the cavity with changes in temperature and pressure. And we have to account for the particle motion as well in our trapping set. And we assume that the particle motion is circular in the horizontal plane. It's negligible in the vertical plane, and we use some empirical model to compare the effect of the particle motion in our measurements to our simulations and match the two up. So this is a sanity check here. We've got our simulated data set on the top and our measured data set on the bottom. You can see for a given particle size, the distribution in the extinction cross sections is quite consistent between the measured and simulated data sets. So when we look at the retrieved accuracies, I've got this is the absolute difference between the input and the measured imaginary refractive index. And as the imaginary refractive index increases from a really small value to a value that's more consistent with black carbon, so something that's really very absorbing, you see the accuracy increase. And relating that back to this initial value of 0.001, for all of the absorption strengths we looked at, from right at the end here, this weakly absorbing one, we are better than that 0.001 value, which gives us really nice relative forcing values. And the retrieved N values as well for the scattering component are quite consistent, and they give you a relatively negligible uncertainty in your relative forcings. So back to these plots, I've plotted here our measured K, or our measured imaginary refractive index. In the solid line, the hatched fill is our theoretical uncertainty that we just calculated from accuracy assessments, and the dashed line is our predicted imaginary refractive index from refractive index mixing rules. So all we've done is input the optical properties of the two pure components, and you know the mass fraction of the particle for a given size, and you can see that our measurements match or agree with the predicted imaginary refractive index, which is really nice. So to summarize, we've made these first single particle measurements for absorbing aerosol particles. We've completed some theoretical accuracy assessments, and we've got an accuracy that gives us a really nice relative forcing. And in the future, we want to explore the kinetics of some photo-initiated chemical processes. And I'd just like to finish by saying thank you to everyone in the Bristol Aerosol Group and to my supervisors, Michael and Andrew.
Thank you very much, Jamie. Do you have any questions? Yeah.
Hi, Jamie. Jim from Bristol. Just looking at your experimental extinction cross sections, it always seems that you have a bit more noise. It's quite subtle, a bit more noise at the larger particle sizes. Yeah, it's very subtle, but I was wondering if you could give that a go.
Yeah, I'm not 100% sure. I think I didn't go into it in this talk, but in the result of using the cavity, you then have a standing wave that builds up within the cavity, and these extinction cross sections then depend on the position of the particle within that standing wave. So there will be some natural kind of breadth to that. Me theory assumes a plane wave, there's no standing wave, so you just get a finite value for each radius and value of the complex refractive index. And so the distribution comes from that standing wave. What we do is we average our cross sections to 1 Hertz intervals, and that compresses the kind of envelope in these extinction cross sections that comes from the standing wave to the me theory limit for a traveling wave. But you do still get some broadening at the higher sizes.
Jonathan, do we have any questions in the chat? Okay, so I just wanted to finish with you, Jamie. So you said you were talking about the accounted for particle motion, and you said you assume circular motion but not vertical. So could you explain why you think it must be moving in a circular way but not vertically?
Sure. So on the imaging camera, we can see some blurring in the horizontal plane,
Okay.
but it's perfectly stable in the vertical plane. So we just think that that's any movement in the vertical plane is probably negligible in comparison. Why we think it's circular, we've done some modeling, so you can derive the equations of motion for the particle for our trapping cell. So for the given geometry of our trap, and you have to estimate the particle charge, and we know the geometry, the voltages and frequencies applied, and you can predict what that trajectory is, and it is roughly circular.
Thank you very much.
Thank you.
Can we thank Jamie again?